the pitch signal that comes from 4 different sensors. And then by analyzing, we can immediately say it's turned to left and command. And here's an example that actually we analyze later on. What if I'm using microphone and I'm using gestures, and I'm saying stop while I'm showing move ahead? What if there are conflicting commands? Now, the other issue is, okay, so what if there are consistent commands? Which commands should be executed? But if there are conflicting, for example, from the security viewpoint, you might have an intruder who's going to intercept a signal, and he will be saying move ahead while the aircraft is close to the edge of the carrier, the ship, and it's going to fall off the board. So how do you potentially deal with this? So again, you design a system that can deal with that. And then you can read about our publication. I have a list of publications. Okay, so now we deploy the sensors. We want to know when hazards occur. So it's really a synchronization problem. So the problem statement is, given a set of wired and wireless instruments and sensors, synchronize all measurements. Clearly, there is related work. There are network time protocols, digital time synchronization protocols, security protocols for sensor networks. A lot of work. There are journal papers about this, tons of publications. What we've done is we said, look, our wired cameras, they can use the atomic clock and they use the network time protocol. Everything is connected via the internet. But the challenge is when you have these point sensors and they have to wirelessly communicate with a PC, how do you synchronize those? So we view them as standalone PCs pretty much. And what we decided to do is that at the startup, the PC, the laptop, is going to send the current time to each of the MICA, these point sensors. And then the MICA sensor, because it has a counter, will update this timestamp every X milliseconds, let's say 10 milliseconds. And then each reading, so after I measure temperature, I'm going to be sending a packet that includes the reading and the counter back to the laptop, which is the timestamp. And then the laptop is going to look at the difference between when the sensor reading is acquired and the time when the reading is received on the PC. And if it's larger than some threshold, in our case it was 350 milliseconds, then the PC and the MICA sensors will resynchronize time again. So that was the procedure. And that worked pretty well. So we synchronized them, and we asked the question, where did these sensors land? So where did they land? Again, our challenge here is we want to determine 3D location of the deployed wireless MICA sensors and possibly other objects in the scene, assuming that the camera locations are known, they are static. Previous work, again, can be split into 2 different areas. One is the 3D object recognition community, that like computer vision community, machine vision, signal image processing communities. And they use, let's say, shape from cues like stereo, motion, shading, and they get a depth map. And there is a different community that deals with these wireless sensors, and they talk about location sensing, where they use radio or ultrasound time or flight lateralization or signal strength analysis. And there are systems like MIT Cricket Indoor Location System and the AT&T BAT Ultrasonic Location System. They are just trying to solve this problem. The problem is very difficult on its own. So what we did, we proposed a fusion. So again, we know that there are different communities, different solutions to this problem. But we said, well, what if we take the stereo approach, the vision-based approach, we compute the depth. Then we use the localization approach. Again, we compute where the sensors are approximately located. Then we perform data fusion, and then we get much better location of these sensors and all the objects in the scene. So that was the basic idea. The way how the fusion works is that you look at the stereo first, and you say, okay, many of you probably know that if you compute stereo, as you go away from the camera, the uncertainty is going to increase. So clearly, the objects that are close to you, they will be more accurately predicted than the ones that are far away. So we computed something called depth uncertainty. And when it came to the sensor localization, for those of you who don't know how this works, clearly these sensors have acoustic and radio transmitters. There is a buzzer, and the sequence goes like this. First, the base station is going to send a message to all the MICAs and say, we are going to be doing this localization. Then sensors C and D, in this case, would send acoustic and radio ranging transmissions everywhere. And then the sensor A would receive the radio ranging transmission. And after a while, it would receive the acoustic ranging transmission because acoustic waves are slower. And it would measure the difference and report back to the base station the difference, which is really used for estimating the Euclidean distance. The challenge was, if you look at the upper right corner, when we used our sensors, the pink line is really what we expected. We had sensors apart, let's say 1 foot, 2 feet, 3 feet, and so forth. And then when we measured the blue curve, the difference was pretty significant. I think the error was about 2 meters. So we tried to compensate it, but it was not very satisfactory. Then we realized that what we have to do is use much more powerful buzzer. And we borrow some sensors, and we get much better results. So here, the distribution of the error as a function of distance between two adjacent sensors shows that we got better results. However, there is a physical limitation. If you take 2 sensors, because the counters have finite sampling frequency, you cannot get better than 30 centimeter accuracy. So there is always some uncertainty. So by understanding the uncertainty issues, we build a fusion mechanism, which really is shown in the middle. I don't have the pointer, but more or less the curve shows the pink or purple graph shows that the uncertainty for the stereo is going up as you go away from the camera, while the localization was pretty much stable for certain range. And remember, this is only single hop transmission. And here on the right, you see that the measurements that were originally obtained by the localization algorithm were improved after fusion by a certain percentage. I think it was by 27%. The same way, we could take the depth estimation from the stereo algorithm and improve it with the point measurements obtained from the localization, and that was about 98%. But if you can find the threshold, which is shown there, there are 2 regions. I think I can use my mouse here. So there is a region where you should be using just the stereo, and there is a region where you should be using the localization, and that way you get the best result. We even built some theoretical models of these fusion parameters so we can predict what should be the fusion threshold for multiple setups. And that really is based on the uncertainties of these different methods. On the left side, you see if we fix the depth map uncertainty, how is the surface going to intersect with the localization that also varies. And then on the right side, it's the other situation. OK, so we know where the sensors landed. We synchronize them. Now we want to do some real hazard detection, but we have to calibrate the measurements. So the problem is convert point sensors and camera raw values into engineering units to enable hazard detection and recognition. For example, degrees of Celsius or Fahrenheit or Kelvin for temperature measurements. And the previous work, again, it's scattered in multiple domains. It's in remote sensing community. They use it for calibration. Robotics, again, you want to build autonomous vehicles, so you want to calibrate your inputs and analyze calibrated imagery. In astronomy, they are very much concerned about calibration because they are looking at the sky and then trying to understand the stars. Military, clearly. So our primary approach was to do a black body or temperature gauge calibration. And the schema that we decided to use is that we either calibrate the point sensors or we calibrate the thermoinfrared camera, and then we use it for calibrating the other sensing modality. So you would say, well, the sensors can be